He holds a PhD in biomedical engineering from Carnegie Mellon. He's an assistant professor at Vanderbilt. He is their AI fellow at the Vanderbilt Lab for Immersive AI Translation. He has received the NSF Career Award, which the undergraduates in here won't know what that means, but people with PhDs will be like, oh, that's a big deal. He also has led a number of DARPA projects, and he received the Best Paper Award at ICASSP, which is one of the most important and prestigious conferences in signal processing in 2022. Best Dissertation Award at Carnegie Mellon as well. That was not in my list of accomplishments. My apologies. Also, for those of you who are in the room, we are giving out certificates for having been here, but we need to know you were here. So we're going to pass around our sign-in sheets. If you've missed it for either this morning or this afternoon, please do sign in. Folks who are online, we've already got your names. We know you've been here. All is well. And with that, I'm going to pass over to you, sir.
Well, hello, everyone. Thank you for that nice and kind introduction, Chris. It's a pleasure to be here and presenting the transformer idea to you all. So thankfully, I was here in the morning and I saw the fantastic job that Professor Huo did. So we are going to kind of pick it back from where he ended. I try to connect these two sessions as much as possible. So a 10,000 feet view of the deep learning and machine learning field in general is that there are 4 different components that we need to be aware of. Any machine learning problem, deep learning problem has this. So you need to have data, you need to have a parametric model, you need to have a loss or objective function that you're trying to optimize, and these 3 will generate an optimization problem for you. And then you need to be able to solve that optimization problem using some optimizer. Okay, so if I understand correctly, yesterday you have already seen like very simple models, and you saw gradient descent for optimization, essentially how to formalize the simple loss and objective. And this morning, we focused the majority of our time on the model, a specific model, and we saw like convolutional neural network as a specific type of models that are very good for images, right? But the rest, of course, you need to have the data augmentation, and everything that Professor Huo talked about this morning fall under that. And the optimizers, we are not going to really focus on it today. And why I am here in this afternoon and what we would like to accomplish together is to talk about a different type of model. Okay. Now, while we are doing that, we are going to kind of revisit these other components as well a little bit. So why transformers? Transformers are a different type of architecture and of neural networks. The reason we are interested in transformers is that they are currently the state of the art in almost any task that you can think of, right? So state of the art vision models used to be convolutional neural networks, but not anymore. They are actually kind of hybrid models between convolution and transformer networks these days, but more like transformers. State-of-the-art language models, of course, we all use OpenAI's GPT, Cloud, Gemini, and so on. These large language models are fantastic. They all use transformer networks. State-of-the-art speech models, Whisper, VoiceBox from Meta, they are also transformer-based models. AlphaFold, this morning, Professor Hu talked about AlphaGo. The same type of reinforcement learning that he talked about was used with transformer networks to predict protein folding, which is a very big deal in biological sciences. So that's also transformer network. You might have seen a video generation, image generation. Sora generates videos based on input text, and those are also based on transformer networks. And even a state-of-the-art robotics and reinforcement learning models are more and more becoming like transformer models. So before transformers, which we will talk about where they come and all that, any of these tasks that you wanted to solve, you needed to use a different type of architecture. For images, you used convolutional networks. For speech, you use recurrent neural networks and like Boltzmann machines and so on. Like there were so many different types of architectures. What makes transformers very interesting and powerful is that now all of these domains are using pretty much the same type of architecture. Okay, so it's, of course, there is a little bit of variation from these architectures, like, but the overall is kind of the same structure. And if you think about human brain is yes, my brain is different than your brain and different from somebody else's brain, but the overall architecture is more or less similar, and we are able to learn a lot of different tasks. So I'm not saying that transformers are bio-inspired, but at least functionally, they are behaving very much like an actual brain that can solve these different tasks. Okay, so what is our goal today? A little disclaimer, this is a transformer network. Hopefully by the end of this day, you will you will understand every single one of these components, and you will be able to actually code it, because I have the demo for that as well. But we would like to understand what are transformers, where do they come from? What is attention? Attention is one of the main mechanisms used in transformer networks. What are queries, keys, and values? What are tokens? You may hear tokenization. What do we mean by tokenization, and so on? Positional encoding, what is positional encoding, and then layer normalization, and finally, how to implement a transformer in PyTorch. Of course, we only have 3 hours together, so we won't be able to dive very deep in PyTorch implementation. I'll do my best to cover, but you will have access to the Colab notebook that walks you through the implementation of transformers from scratch. Okay, so as I mentioned, transformers are neural network architectures that consist of a new type of architecture that are ubiquitous in different domains, and they consist of composition of transformer blocks. Okay, and now what is a transformer block? Well, a transformer block is a computational, a permutation equivariant operator. Don't worry if you don't know what permutation equivariant is. We will see what we mean by that. That consists of a few different components: layer normalization, multi-head self or cross attention, feed-forward neural networks or multi-layer perceptrons, and skip connections. So here I show you a transformer block. Again, don't worry about it. We will go through and we will create every single element and try to understand it. But before we do that, where did it come from? Okay, that's the first question. So we know what transformers are. Now, like, where do they come from? They come from this paper, Attention is All You Need, that was published in NeurIPS, the Conference on Neural Information Processing Systems, in 2017. And it's one of the most cited papers in the scientific community, overall, in the scientific community. Okay. So as you can see, even the title of the paper is saying that attention is all you need. So attention is at the heart of transformer networks. We want to understand what a transformer network does. We need to understand what attention is. But for us to be able to answer what is attention, we need to go back a little bit more in time and ask ourselves, what are the origins of attention? What do we mean from attention? And we can see that the origins will actually go back to 2014. And because 2014 in the field of AI is considered ancient, right? We are going to actually have a historical type of detour to understand some of these concepts. So this is kind of a parenthesis that walks us through what is attention. So you saw this picture this morning, the godfathers of AI, Yoshua Bengio, Jeff Hinton, and Yann LeCun, the happy guy in the video that Professor Huo showed. And one of my favorite, I think the all-time greatest of all-time person in a field of AI is actually Yoshua Bengio. He's a very prolific author, has worked on a lot of different topics, and he was the recipient of the Turing Award alongside Jeff Hinton and Yann LeCun. So we see a lot of Yoshua Bengio in his footsteps in transformer networks when we talk about it. Going back to even before 2014, 2003, one of the earliest papers that used neural networks for language modeling. Okay, so this is, I shouldn't say one of the earliest, it's one of the early papers that used neural networks for language modeling. And you can see the first author in this paper is Yoshua Bengio, 2003, the young Yoshua Bengio at the time, wrote this paper. And what this paper does is actually quite similar to what our language models do these days. Okay, given a few words or given a sentence with the last word omitted, predict what is the missing word. Okay, so you have a sentence and you essentially would like to read this sentence and predict the last word is missing or whatever. Like you have a string, the last part is missing, you would like to find the right word to put there. Okay, so what can you do? If you can see on top of this figure here, what you would like to predict is the probability of a certain word being at a certain location, let's say the last word of the sentence, given the context, given the entire sentence. Okay, so it seems like it's been already done in 2003, but actually there are a lot of issues. So one big issue with this paper was, of course, we didn't have as much compute as we have today, but more than that, there was a fixed context window of length n. So that means like you need to always analyze a sentence with n words in it and try to predict the next word. So there's a fixed window of context that you can have. So why is this problematic? Let's consider this paragraph that says, I grew up in France surrounded by the charm of cobblestone streets, blah, 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 blah. It goes through a lot of things, living in the country, so rich in art, literature, and so on. At the end, there is a sentence that says, naturally, I speak French, right? So now let's do this fixed context size and see what will happen. I put the first context window. I grew up in France, surrounded by blah, blah, blah. An aroma of fresh baguettes. This empty space that we need to fill. Of course, now this is a well-posed problem. I can put laughing, drifting, feeling. There are certain words that can fall there. So we will be able to learn this with a neural network. You can generate a probability distribution over words that tell us that these words should have high probabilities. But if we go to the end and culture shaped by a worldview and blah, 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 naturally I speak. Based on just this concept, I can speak any language. Right? There is no information about France here. So this is an ill-posed problem now. Like I should get uniform distribution over all languages in the world. Okay? So there was this lack of being able to increase the context. And of course, if you wanted to increase the context and have very large context, then that would have made your input become very large. Or you wouldn't have been able to deal with different size contexts. Okay, contexts in that case. So almost 10 years later came the another paper, and this name should be familiar, Ilya Sutskever. He was one of the founders of OpenAI, right? He and Sam Altman do it together. So, and this he has done while he was at Google. It's called recurrent neural networks for sequence-to-sequence learning. So recurrent neural networks were kind of the hot topic around that time, like actually starting 2006, 2007 till like 2014 and so on. They were the main architecture that was used for modeling sequences, whether you have temporal signals, whether you have words and so on. And one of the most common type of recurrent neural networks that's used in the literature is long short-term memory, or simply LSTM. Okay, there are other variations, GRU, gated recurrent units, and so on. These are different types of recurrent neural networks. This paper uses a recurrent neural network to do language modeling, and in particular to do sequence-to-sequence learning. And that means, for example, if I want to translate English to French, like have a sentence that's in English, it comes in, it gets encoded. And then there is this vector that's the context vector. It's the essence of the English paragraph or sentence that the model has seen. That goes into another model that's called the decoder that tries to translate exactly what the English sentence was. Okay? And all of these blocks that you see here are recurrent neural networks. That's beyond the scope of this class. We don't want to talk about recurrent neural networks, but just think about them as some sort of a recurrent computational units that you're applying to different words. Okay? So this paper was revolutionary, and a lot of papers after this used recurrent neural networks for doing language tasks. But a beautiful observation was made in another paper that we will talk about that said, hey, this idea of recurrent neural networks is good. We agree with that. But don't you believe that if we want to complete this word, for example, and we have this very long context, we need to essentially remember everything from the first sentence till the last sentence. And what that means is that all this information is kind of bottlenecked through one vector. There is one vector that goes from this computational block to the decoder, right? This one vector needs to hold the information for that entire paragraph, okay? And that's hard. That's too much to ask from a fixed dimensional vector. If your context grows, you're trying to squeeze a lot of information, growing information into a fixed size bottle, which is your vector. And it's going to overflow, like you won't be able to carry all the information. So this was noted. The encoder's output is fixed dimensional. The context, it's usually referred to as the context vector, and it can't hold all the information. Okay. So again, this is 2014. And now, 1 year later, we have another paper from Bengio's group. That's called Neural Machine Translation by Jointly Learning to Align and Translate. So what this paper does, actually, let's look at the quick sentence here. It says, intuitively, this implements a mechanism of attention in the decoder. The decoder decides parts of the source sentence to pay attention to. So what is this saying? This is saying that let's not make just this vector to be the bottleneck of information. For every single word that we would like to decode, let's go and look at what are the previous words or what are the previous parts of the sentence that was relevant to what we want to say here. Okay. And in the example that we had, I grew up in France, if you want to say, I speak for that word, it will immediately go back and say the first few words or the first sentence is the most important part of all the context to pay attention to. So it's kind of cheating, right? You have all the information. Of course, you don't want to analyze all that information. You want to pay attention to parts of this information and then make your prediction based on that part of information, okay? And that became the state of the art. Actually, there was a very fierce competition between this group and Ilya Sutskever's et al. At Google. They were in competition, and there is a nice interview with the first author, how he was stressed out to actually publish his work before Google publishes on it, right? When he was a PhD student. So let's quickly just look at some equations here without knowing what these recurrent neural networks are. If you really think about this as computational blocks, each computational block get a context, get the current word or currently predicted word. Let's say at 0 time, we don't have anything. This y0 is just beginning of sentence or just a beginning token. And then it gets a previous state that tells us like what has been said so far. Okay? So now if you look at it, it says that the state for the next block is going to be the state from the previous, a function of the state from the previous block, the predicted word from the previous block, and the context at the current block. So now what is context CI? It's essentially a linear combination of these H's, which are our encoder's information. The blue sentence, I grew up in French, the encoded vectors for all of that. So now, like, what is this alpha ij? They define this alpha ij to be essentially a probability distribution over all these h's. Which of these h's do I need to pay attention to? Okay. And how do we calculate that probability distribution? As a function of similarity or alignment of the model between the current, the previous state that we saw, and all the h's that we have seen in our encoder. Okay. And this was referred to as attention in 2015 at an ICLR paper. ICLR is, again, another very well-respected conference in AI and machine learning called International Conference on Learning Representations. Okay. And it's a fairly newer conference compared to others, but it's actually highly impactful. It's one of the top 10 venues across all scientific fields. Okay. not just CS or computation. Okay, end of historical detour. Is everyone still with me? Do you understand where attention is coming from? Okay. Questions? Yes. Oh, it's all about attention. Why the name is transformer? I don't know. That's a good question, right? That's a good question. And I think the logo for it was the Transformers, the animation or the cartoon of Transformers. It's the robots that turn into cars and so on. I think it had something to do with that. I'm not 100% sure about that. I don't know. Right. Could be that could be another thing, but autoencoders are like that too. Why don't we call autoencoders transformers? I don't know. Yeah, but good question. I don't know the answer, frankly. Yes. So, yes. Sure. Yeah. Yeah, it can. Yeah, so it's not just a sentence, it's the context window. There's a good question. Let me try to, let me rephrase it so we all understand. The way that I talked about it, I have a sentence and I am missing the last word. That's really not the case. I have a context window, which is a bunch of words. It can be in the middle of the sentence. It can be anywhere else, right? It can be actually half of the first sentence and another half of another sentence, right? But the important point is that the last word is missing. What I want to do is, given the context, what is the next word? Okay. And if I have the next word, then I can move my context based on the prediction that I have, move my context one more, and now I will have the context plus the word that I predicted as my new context. And I send that to the network and ask, what is the next word? And a model like this is referred to as an autoregressive model because it's regressing on its own output. It predicts an output, you bring it to the input and send it in again. Is that clear? That's exactly what ChatGPT does, by the way. Yep. Yes. Yeah. The next token. So yeah, let's put a pin on that question because we will get there. So what they do is they predict, given current number of tokens, whatever you have, what is the next token? That's exactly what these autoregressive models do. But for us to be able to understand what do we mean by a token, we need to first understand what tokens are. So I'll get there. Okay. Thank you. So that's the end of our historical detour. So now I want to start talking about a transformer block. So my approach towards this session is a bottom-up approach. What I mean is I'm going to actually create different components first carefully, and then I'm going to use those different components to create the gigantic model, which is the transformer model, right? So I usually use this figure in my deep learning classes to talk about a perceptron that you saw this morning, a neuron, and how a deep neural network is a combination of a lot of those neurons, right? But if we're really talking about transformers, we still have something that looks like that, but it's not as simple as that. It has different components. A transformer block is, I can think about it as a Lego brick that has self or cross attention, residual connection, feed-forward model, layer normalization, and dropout, which thankfully Professor Huo talked about this morning. And like, if we understand this block, then we will be able to put them together and build everything that we want. Okay, so let's start understanding what that block of computation is, what that transformer model is. Okay, so if you look at this transformer architecture that you see here, there is an encoder, very much like that recurrent neural network encoder that we have, and there is a decoder. For the sake of our conversation, let's just focus on the encoder part for a second. And you see that there is something called n times this, okay? So what we see here is a transformer block. And our encoder has n of these transformer blocks, okay? composed together. Very much like in your convolutional neural network, you had your layer 1 convolution, layer 2 convolution, layer 3 convolution. These, instead of convolutions, we have transformer blocks and we compose them together. So what is this block? Here's a depiction of this block. We have some inputs. These inputs are vectors. We have n d-dimensional vectors. These are referred to as tokens. We have self-attention. We have residual connection. We have layer normalization. We have multilayer perceptrons, shared multilayer perceptrons, another residual connection, and another layer normalization. Okay. Right now, it's just the blueprint. Okay. Now, I want to go and start talking about what is self-attention, and then we will do one at a time, and I'll try to understand everything. So what is self-attention? The way that I like to motivate the idea of self-attention is through the idea of message passing. Okay? In the field of deep learning, message passing is a general term that can be referred to the aggregation of information between different components, right? So let me use, you just saw convolutional neural network, so it should be very easy to describe. Think about your image. I'm showing you essentially an image here, and the xi-1, j-1, or xij is the grayscale value of that image. We saw this earlier this morning. Okay, and then I have a convolutional kernel that we saw, those Gabor filters or learnable features that you saw. And these have some values. I'm calling them wijs. Okay, I have a 3x3 convolutional kernel, very much like what we had in the morning. So what will happen is that, of course, you saw that you go and you calculate the inner product of a vectorized version of this and every parts of your image, and that will be the output of your convolution. Okay? But I can think about it as, well, at each layer, when I apply a convolutional kernel, I am aggregating the information from the neighbors. And what I mean by that is my center node is going to get updated according to an equation. What is that equation? That equation is simply this inner product between this kernel and the neighborhood. Okay? So it's essentially the same thing, right? It's exactly convolution. But now I think about it as, well, what's happening is that I am updating my self feature. I'm updating xij. And I'm also aggregating the information from all my neighbors. I'm essentially asking my neighbors to send what they have to me. And I decide how much weight should I put to each neighbor. And those weights are the convolutional kernel parameters that we have. Okay? Still convolution. So why is this idea useful? Because I can think about attention as a different way of doing message passing. Okay? So now that we understand what message passing is, we're just updating the features of a node. Yes? Oh, good. So this is a very good question. Thank you. This is essentially at what layer you are, right? So I'm saying that at the next layer, if you're doing this convolution, your feature is going to be a linear combination of the self feature and all the neighbor feature according to the kernels that you have. It's different layers. Okay. So now, maybe a little bit more formal, it's not formal, but at least a little bit more careful definition of message passing. It's a fundamental concept in deep learning where information or the message is exchanged between components or nodes of a system to update state or representation. Okay. And so what we have is usually this form. The updated feature for node I is going to be the previous feature for node I, a function of the previous feature for node I, and the features of the neighbors of node I. Okay, exactly for the convolution, we saw that this is what happens here, right? This, I can think about what I wrote in the next slide as a generalization of this equation. Okay, that function is simply linear here, but in this case, I wrote a general function f. Okay. So, and this idea is usually used in graph neural networks. So when your data lives on a graph and you would like to apply a deep learning model on a graph, this is the idea that you use. The idea of a message passing is what you use. Let me give you an example. The election is coming up, let's say, was coming up. Like I want to predict what will each person vote for. Are they going to vote red or are they going to vote blue? Right, black. Hopefully not. Right, so blue or red. So then if I can describe every person with some features, let's say I have access to social media, right? And I scrape a lot of information from that person, male or female, what age, all the information that they have, what books do they like, what movies do they like, and all that. And I try to make a prediction based on that feature, only that feature, okay? I get some prediction, right? Like, and say the accuracy is going to be X, for a second. Now assume that instead of just doing that for a single person, I go and I look at not only that person, but also the friends that they have on the social media. And I look, what friends do they have? What is the features that their friends have? Right? And then I aggregate the information. We have this saying that a person is kind of who they hang out with or who their friends are. Like there are sayings like that in different cultures, right? So when you aggregate the information from all the neighbors or all your connections, you have a much richer feature to describe that person. And you will be able to predict the whether they are going to vote blue or red much more efficiently or much more accurately. That's the idea of message passing, okay? So now here we say, like, we have, these are the messages that being passed, the information and being passed, we update the information of a person, and then we do our classification based on that. Okay, so now I'm going to tell you that attention is a very specific type of message passing. Okay. So what is attention? As it was described in Attention is All You Need. I think the problem can be best described as if you are seeking for knowledge in a specific domain, let's say deep learning. You're all here, so you are all interested about deep learning. Say you would like to understand the content of all books about deep learning. Okay, that's your query. You would like to understand knowledge. Okay, then you go to a library, and there are millions of books in the library. Think about those H's that we had as those books. Okay, so each book has a metadata that talks about the title, some keywords, and so on, right? So what do? You actually go and try to match find the keys that are aligned with your query, right? I want to find books that are about deep learning. So you look at all the metadata for the different books, and you do a search based on that, and you retrieve a set of relevant books based on the information that you have, the query that you have. What do you do after that? You go and you read those papers. You read those books, correct? So after you retrieve these books from the library, you go and retrieve the books to read the books to find what is the value or what is the content of these books. And your knowledge about deep learning is going to be an aggregation of these contents of these books. Okay, this is the content of each book is referred to as value. Okay, are we all following what is query, key, and value in this context of a library? Okay, now imagine that instead of a library, you have these nodes are people. You have a query. You have a bunch of friends that you're connected with. And you go with this query to your friends, and each friend has a metadata associated with them and has a different message that you can, they can tell you about that topic. So you essentially look at, based on your query, you look at who is the most knowledgeable person, and then you ask their opinion, and you aggregate the opinion of your knowledgeable people. But in such a system, each node will do that. Maybe your friend has some question that will ask for your knowledge about something, and they aggregate your value, okay? So let's mathematically formalize this. Each node I is going to have a feature xi. We are going to create a query simply as a linear function of the xi. Xi is a d-dimensional vector. This wq is a, let me try to write it here. WQ is R D Q by D. And you create a query for that node I. You create a key in the same way. And this DQ, this is not a typo. This could have been DK, but DK and DQ must be equal to each other for a reason we will see immediately. So this WK is also RDQ by D. And then you have this value, which is also a linear function, and it's going to be RDV by D. So these are learnable parameters. you have a parametric function. Again, the model, we are designing it. We are going to learn what these are eventually. Okay, but for now, assume that they're just the parameters. And then if we have the query key and value, we can go and say your output or updated information for node xi should be the aggregation of the values from all other neighbors. Okay, with some alpha. What are these alphas? These alphas are exactly the attention that we were seeing before. You need to first aggregate these, but to aggregate them, you need to know which neighbor to rely on, who to pay attention to. How do we calculate attention? I said that in attention, we create a distribution over the all the neighbors that you have. So then in Benjio's paper, we saw that it was an alignment term between the state and the S and H's. So here we just say like the attention that I needs to pay to J, node I needs to pay to node J, is a normalized similarity between the query of I and key of J. I mean, exactly like you want a book, you look at which book has the metadata that's similar to the book that you are interested in or the topic that you are interested in. That's the similarity. How is this similarity measured? Well, you know, we can always rely on cosine similarity, right? If we wanted to have cosine similarity, we needed to essentially have the inner product divided by the norm of Q times norm of K. But we can say the inner product is a notion of similarity, assuming that these Q and Ks are more or less normal, okay? It's not exactly cosine similarity, but I can treat this as still an inner product between two vectors. So the angle between two vectors as a notion of the similarity. Okay? So with this, essentially, we have all the equations that we need for attention. Is this clear? Any question? I think this is important. Maybe we can spend some time. Yes? Yes. Yeah, so essentially, if I had like all ones for these, so this is a d-dimensional vector, this is a d-dimensional vector. If I had all ones and I calculate the inner product, I'm going to get dq, right? And then if I calculate the norm of that, it's going to be dq, okay? So this normalization is simply if I have that divided, each one of these divided by the square root of dq, if I calculate the norm in the case that they're all ones, then norm is going to also be 1. So this is simply a normalization that avoids things to explode, numerically explode. Very good question. So, yes.
And this key is needed for other nodes comes with this node thing.
Beautiful. Yes, that's exactly it. Yeah, the key is for other nodes. The query is for you to go and seek information, and the value is what you share with everybody. Broadcast. Okay. So as you can see, actually, I have formalized everything in the sense of a graph already. Like this is graph neural networks we are talking about, but you thought that we were going to talk about transformers. Well, it turns out that the transformers can be formalized as graph neural networks, okay? With the difference that a transformer is a set neural network. You can have an input set, okay? You don't necessarily have connections between different nodes. You have just a bunch of nodes, okay? You have x1 to xn, okay? But what do I mean that transformers are set neural networks? You have a neural network. This neural network is a computational operator. It's a parametric computational operator. It gets a set of nodes, set of d-dimensional vectors as input, and it gives you a set of d-dimensional vectors as output. That's what I mean by a set neural network. Okay. So now there is no information about edges. Here it seemed like I talked about neighborhood, and I said the summation. Here, this summation was over. Where is it? Here. This summation is over the neighbors of node I. Okay. If I don't have any information about connection between nodes, I can think about the set as a fully connected graph. And I can essentially let everybody to talk to everybody. I can let the message passing to be between all the nodes that I have. And this is usually referred to as all-to-all message passing. All your nodes are going to do message passing together. Okay. So, and if this is the case, then I don't need to have that J in neighborhood of I or neighbors of I. I have simply a summation over all my nodes. Okay. And voila, we have our self-attention. This alpha ij is referred to as the self-attention matrix. Why matrix? Because you know we have alpha ij. So if I define a matrix A that its ij element is alpha ij, this is the attention matrix. Okay. So now a pictorial way of depicting the same thing. We said that each node is going to generate a query, and all the nodes are going to have keys. So if I want to like compare, like understand how to mix information from this node 3 to node 2, I calculate the inner product of query and query of node 2 with key of node 3. I need to do a normalization with that softmax, the e to the power that we have. And then I get my alpha 2, 3, which is telling me how much attention must node 2 pay to node 3. And then I multiply that by the value of node 3 and bring that information and aggregate it to node 2. And I do it for all other nodes. Okay. So now I told you that transformer block is a permutation, is a set operator. And I also told you that a transformer network is actually a permutation equivariant computational block. So what do I mean by that? So if you have your node 1 to node 4 have features x1 to x4, I send them in and I get y1 to y4. Okay. Now remember that this is a set that I am sending in, so the indices are arbitrary. I can move the indices around. Okay. So if I had sent x2, x4, x1, x3 instead as location 1, 2, 3, 4, I will get y2, y4, y1, y3 at locations 1, 2, 3, 4 in the output. So if you permute your inputs, your outputs are going to be permuted the same way. This is referred to as permutation equivariant model. Okay. Yes. So attention, when we say attention, we mean self-attention, right? There is another alternative. Sometimes we differentiate self, we actually call self, and that's to differentiate it from cross-attention. There are two types of attention, self-attention and cross-attention. Okay? What we talked about is simply self-attention. We will see what cross-attention is in a few slides. Okay? Absolutely.
So, that weighted sum of the values that all neighbors.
Correct. It is exactly that.
And then the weights are the similarity, like somehow like the similarity of what you were asking, not those neighbors.
Correct.
So why I is simply the value that you're going to get from your neighbors.
It's in fact a convex combination of the values because that's a probability vector. This alpha is a probability, so it's a convex combination of the values of all your neighbors. Yes.
I understand there's a naming convention. There is keys, queries, and values, right?
Mm-hmm.
But keys and queries come from the same thing. They are connected to the same thing. They are the same size, and they get multiplied, and they are not used individually. So if I gave you the transformer, but if I told you that queries are keys and keys are queries, would it work the same?
No, they can't be the same thing, right? Why they can't be the same thing? Because so if queries and keys are the exact same thing, then what you will get here as attention is essentially a one-hot vector, because your query is going to be the most similar to your own key.
Well, I'm not saying they are the same. I'm trying to switch them.
Oh, you switch. Oh, yeah, you can call them whatever you want. Yeah, that's fine. Right.
So I can give you keys as queries and queries as keys.
You can give me keys as queries and call them different, but like remember that each node uses like it's important, I think what Professor Sekman said is important. Each node generates a query to aggregate information from other nodes, generates a key such that other nodes can ask it. So I think your question is why are we calling these queries and keys? If I revert everything, I called keys queries and the other way around, nothing changes. I agree with you, nothing will change. But conceptually, like if we go with what this example that you have, like a node will come with a query. That's what the information it needs, right? And then like the key is like the information other nodes have, and you would like to kind of calculate the inner product between those two. Now, if you're saying that why don't we do queries with queries, that's a different situation. If I do queries with queries, then attention will be one hot.
I'm just trying to understand if I am missing something, but they are connected exactly the same.
What do you mean they're connected?
Queries and keys are connected in this like transform model in exactly the same way, right? They are all connected to the XI, right?
Correct.
And then they are going to do other side. They get multiplied with each other and they go to the other side.
Correct.
So they are symmetrical with each other in a way.
Correct. Your attention is going to, if you switch the keys and queries, your attention is just going to simply be a transpose of what you have calculated. Correct.
It's said that based on
X. Correct.
but we get different because of different
Because of the different WQ and WK and WV. These two. Yes, keys and queries are going to be different, definitely, like generally different. They can be the same if like the network learned that that's the best thing to learn, but generally speaking, they are not the same. Right. And one more important point here is that I can ask this question: is Y a linear function of X? Right. So remember, like when we are designing neural networks, that nonlinearity, sigmoid, ReLU, or anything else that Professor Huo talked about is important. If you don't have that, you're simply composing a bunch of linear layers together, and composition of linear functions is a linear function. So you are not going to be able to learn the more complex features from your data. You need nonlinearity to be able to learn complex features from your data. But is this simply a linear function of, is Y a linear function of X or not? Well, I can put instead of Vj, I can simply put the WVXJ. So it seems like that part is linear. The question is this alpha constant? The answer is no. This alpha is a nonlinear function of the X through these keys and queries and through this function that we have over here. So overall, Y is a nonlinear function of the input x's. Yi is a nonlinear function of the input x's. Okay, that's an important point. Can you? Yeah, MLP is not linear, so that's my point, right? So here, if I have W1 X, and then I simply say this is my layer 1. So this is my input, okay, and I call this X1. And then I call X2 to be W2 X1. I can write it as W2 W1 X0. And this is, I can call it simply a W prime X0. So it's essentially what I have is that having 2 layers is the same as having 1 layer. If there is no nonlinearity. But the moment I put nonlinearity, I use a different color for that. And I call it sigma. This sigma can be the sigmoid that we saw before. it can be tangent hyperbolic, it can be sigmoid, or it can be ReLU. Then what I have is this. And then this is different from simply one layer. Thank you. Okay. So where were we? We saw that. Okay, so if we go back to the layer, this self-attention that we saw, if we look at the actual block that's shown here, it says multi-head attention. So far we understood what's self-attention, but it seems like we have something that's a little bit more intricate. It's multi-head attention. What is multi-head attention? So the same idea of having the attentions, keys, queries, and V's, we can do it in parallel multiple times, H number of times, H being the number of heads. Why is this the case? Because maybe each node has multiple types of queries. We would like to aggregate different types of information from the neighbors, okay, from the other nodes, right? So each one of these W's now, I separate these heads. I calculate a self-attention in head 1 to head H. And after I do that, I simply go and concatenate the output of all these self-attentions. So I get Y1, Y11, Y21, all the way to yn1. I get Y12, all the way to yn2, and so on. I concatenate all of those together. And I apply a linear layer at the end. Why do I do this? This is what the attention is all you need paper did, and it works really nice in practice. Again, I think Professor Huo talked about it, that people go and see like what method was the winner of a certain competition or certain challenge, and then that sticks because that seems to be working. And if you change it, you usually perform a little worse. That means like this is kind of a local optima of architectures, if you want to think about it that way. But nevertheless, so here we have our inputs. We have a self-attention for each one of these. For each one of our inputs, we calculate the self-attention between all the nodes. We have H of those. We concatenate the output of each one of them, and then we send them to a linear. So in other words, I get the outputs of these, concatenate them, and send it through another linear function. Okay, and that's what's referred to as multi-head attention. It's really nothing. It's simply parallelizing the information, parallelizing the self-attention so you can have multiple types of queries per node. Okay. Do we all understand what's multi-head attention now? Okay. Questions? Yeah, so each node, like if we go with one self-attention, each node must have only one type of query. So that one type of query is the only thing. That WQ matrix that you're finding is going to encode one type of query. Now I can say each node can aggregate can have different types of queries. Okay. So let me give you an example. The node in the library example that I told you, I may go to the library and not only have questions about deep learning, I may have questions about philosophy, right? So then if I want to look for these different informations, what do? I do a key query match on deep learning. I do a key query match on philosophy. I go and I aggregate the information from deep learning books, from philosophy books, and then my knowledge is going to be a concatenation of these knowledges, these different types of information that I have acquired. That's exactly the rationale. Correct. Correct. So you're just simply allowing flexibility for the model to learn it if it needs to. That's precisely it. Yes. Getting multiple, that's a very good way of putting it. It's like getting multiple types of views from your neighbors. It's like you go to your friends, you don't just ask them one type of question. Like you don't just ask their political view, you also take them, ask them about their favorite food, if that's relevant to the task that you're going to learn. Okay. One node will have multiple queries based on this, right? So each node, each head is going to have its own query. So QI1 is the query of node I for head 1. Okay, and then there are going to be keys for head 1 and values for head 1, and we go through that message passing schema and find a value at the output of this for node I. But this node, the value that I'm finding is going to aggregate the information based on the query that this query 1 that this node has. And now I can have query 2, query 3, all the way to query H, which is the number of heads. Beautiful question. So this is a very deep question you're asking. There are actually papers in the literature, very recent papers in the literature that try to induce different information to be encoded with different heads. If the information is redundant between different heads, you're essentially wasting your parameters, right? So there are ways that you can go and you can say, hey, the distribution of the queries that I'm generating here should be different from the distribution of the queries that I have in other heads. And the pairwise distance of these should be maximized. So those ideas are already, people are paying attention to. But I thought that because we only have 3 hours, maybe we shouldn't go there. But that's a very deep and very good question. Thank you. Okay. So let's look at this attention and write it as in the matrix form. Well, we saw what queries are. So this query matrix now is going to be a n by dq matrix. I'm writing that q to be n by dq. And k is n by dq as well. So when we calculate the transpose, it's going to become dq by n. And the numerator qk transpose is going to be an n by n matrix. Okay, so this is going to be an n by n matrix. We have that normalization to avoid the explosion of numerical values. And then we calculate the softmax. What is this softmax? This softmax is simply that function that we saw, e to the power, softmax of u. The ith element is going to be e to the power ui divided by sum of e to the uj's, right, over j. So it simply says that if you give it a u, it provides a vector u, it will provide a probability out of it, or a PDF out of it. Okay, so now this softmax is applied to every single row of this n by n matrix. Okay, so this is a row-wise operator. And here, if you want to implement this, we need to be a little careful, because if you use softmax naively and you have very large values for u, when you're coding this, you may actually get nans. Right, that happened to me a lot of the times, like when I was doing my PhD, and it took me a while figuring out why this is the case. So here you will see that if u is very large, you are calculating e to the power of something that's very large, and simply calculating that is going to give you an overflow, right? And that's the issue that happens here. So there is a trick called the log sum exponential trick. And it just simply tells us that this is going to be exactly equal to if you calculate e to the power ui and you subtract the maximum value of ui's from your vector. And this should be fairly easy to see why this is the case. I mean, I'm simply having e to the ui divided by e to the m. And in the denominator, I have j, e to the uj divided by e to the m. I can factor the e to the m's and cancel them. So this is exactly equal to that. But this is much more numerically stable because you don't get very large values in your exponent. OK, so this is just simply a practical trick for us. Now that we know what self-attention is, let me be sure that we have enough time. Good. So what is the computational complexity of this self-attention? So let's go through different operators. We know that we had this matrix form of attention between keys, queries, keys, and values. And it has the qk transpose divided by square root of dk. So this is an n by dk or dq, doesn't matter. This is this transpose is a dk by n. And this matrix product is going to have n squared dk operation. Okay, So this is a quadratic in n. Let's look at the softmax. You're calculating a softmax of an n by n matrix. This is simply an exponent and a summation. So that's going to be n squared because you need to do it for all elements of your matrix. And then the last one is the multiplication. This whole thing becomes an n by n matrix, and you're multiplying this n by n matrix with this value matrix. And that's also going to be n squared dv. So if we look at the overall computation, excuse me that I didn't use the max of these two, but let's, for the sake of being complete, I just wrote the n squared dk plus dv. So we know that that's the number of operations that we need to do. So what is this n? N is the set size, the size of our input set, right? So that means, like, if you're talking about, for example, language models, this is the length of the prompt that you're providing, the number of tokens. And the more tokens you have, the larger n is going to grow. And if it is quadratic with respect to n, your attention, this is going to take longer and longer the more context window you have. In fact, this is a big challenge for even our large language models. Our large language models try to increase their context window, try to increase the token size that you can send to the model, but that comes at a computational cost. So this n squared is going to be really bad for them, okay? So yeah, this is just saying that the order of computations that I have. Like, I'm using it as the order of computations that I have. This is an O. It's called order of computations. This is is n squared dk. Correct. Sorry. Yeah. Okay. Sure. Like, you can. The reason I am using this is because I wanna. I'm really not talking about formal computational complexity. It is n squared as a number of n, but I want to also understand what is its dependency on d. It's going to be linear on d, quadratic in n. Okay. It is. We will see why we have this. Just one more second. I want to turn this into something that's not quadratic in n, and that we will see why I kept them. But, like, yes, we should just think about it as it is n squared, which is order n squared self-attention, when n is the number of tokens that we have. Good question. So now I want to mention that there are a lot of, again, the title of the workshop is mathematical AI. So so far it seems like AI has, like, very simple math and not much meat, essentially. But if mathematics is the meat, so we can use mathematics and very deep mathematics to try to turn this quadratic function into linear function of n. Okay, there are a lot of papers on that. So let me just quickly walk you through the high-level idea. So I can write that equation that we have for this self-attention, a generic form of that equation as a similarity between queries and keys divided by normalization. Essentially normalize that, and this normalization is over the rows of this K matrix. Okay, so this is a different way of writing what I had there. Okay, that softmax is essentially calculating the similarity and doing a normalization. So now, is anyone familiar with kernel methods in core machine learning? So before neural networks became hot, there was this beautiful mathematical area in the machine learning community called kernel methods, right? And it's very different from the convolutional kernels that you saw. Kernel methods were ways of designing nonlinear machine learning models before deep neural networks. And they were, like, very popular from, let's say, around 2000 to 2010, around that time, before neural networks became hot again. And a big idea in kernel methods is that you can transform your data. You can define a similarity between any two type of vectors, for example, by first sending them to the so-called the kernel Hilbert space. Like, let's just, this is a nonlinear transformation of your signal, and then calculating the inner product in that nonlinear transformation space. And this is going to define a notion of similarity between your two vectors. Okay. Now, of course, in kernel methods, you don't necessarily have to have an explicit mapping to a nonlinear function, but like we can talk about that for another day. But now, if we do this, define this similarity between such phi and say it's simply phi q transpose, then something interesting happens. Okay, we can rewrite that the attention that we had over there as phi q transpose divided by these. And now, because I can first calculate this phi k transpose v and then go and calculate this phi q, something interesting happens. And what that is I can show that if you first calculate this and then calculate the other multiplication, your computational complexity drops from n squared to n d prime dv, where d prime is the dimensionality of your phi, the output, the image of your phi. So this is why I said like I kept the d's around, because I wanted to see that there is no free lunch. This is a famous saying in machine learning, right? So I have three terms, n, and d. I need to have n squared d, or I can have n d squared, right? And this is exactly what's happening. I essentially get n d squared. But the good news here is that now I'm linear in n. I can have as long of an input prompt as I want, and my computational complexity is not going to change. Right? I'm going to be as fast. So this is a core idea. And now you can imagine what should we choose for this phi, and a lot of different papers come from, and tell you better ways of creating this phi matrix, this phi mapping, this nonlinear mapping. And the original paper that introduced this was an ICML 2020 paper, and they simply used the nonlinear activation ELU of x plus 1. And again, like this was kind of only the first paper in the domain. And after that, there has been an explosion of papers in the community that talk about different and more efficient ways of creating attention matrices. They're all linear or subquadratic, at least, if not linear. Okay. Just for a time check, how long do we have for till the end of the first session? 3 is. Okay. Okay. Sounds good. Okay. So we saw self-attention, we saw multi-head attention, we saw the complexity, computational complexity of the attention, and we said like there's quadratic, and we need to have linear methods, and other papers are doing these linear methods. Yes. 3. Okay. Okay. Sounds good. So I need to talk about one more thing, 2 more things before we are able to finish that simply self-attention block. And one is the idea of masked attention. So what is masked attention? Maybe there is some sort of a structure in our data that we don't want all the nodes to pay attention to each other. We would like some nodes to not pay attention to other nodes at all. Okay, I would like to enforce some sort of a silence between certain nodes. I don't want them to communicate with each other. How can I do that? Remember that the attention matrix, this A matrix that we had, is an n by n matrix. I can define a mask that's also n by n, and it has value 0 if token can attend to token I can attend to token j. So mij is going to be 0 if I can talk with j. Or it's going to be negative infinity otherwise. Why do we need negative infinity? We need negative infinity because we are adding this mask to or what we had as our attention before. So we have this plus m, and when we have negative infinity, the element is going to become negative infinity. What is e to the negative infinity? 0. So this simply is going to zero out the attention that we had between node I and node j. Okay. So now you may ask, okay, that's fine, but why would you want to do this masking? Like, yeah, you can do it, of course, but what is the rationale behind doing it? If we, for example, are doing text NLP, natural language processing, we are going to generate text 1 word at a time, okay? So if I want to do the prediction of what should be the next word, my current word needs to only see the previous words. It cannot see the future words, right? So essentially, when I'm training these models, I send an entire sentence in, and I have this entire sentence shifted in the output. But if I provide the information and let everybody talk to everybody, the network can simply cheat and go and predict the next word from the input, right? I want to avoid the network to look at the things in future. And at every token, I want to only be able to see the previous tokens to be able to do future prediction, okay? And this is usually referred to as a causal attention, that you are saying essentially each token need to pay attention to the previous tokens, not the future tokens. So this is one reason you may want to do it. And this is an example. Life is short, eat dessert. So if you simply calculate the inner product between all of these queries and keys, you get a full matrix, but of course you want only each word to pay attention to the previous words, right? Makes sense. What's another example of, like, why else would you probably be wanting to do this mask attention? Remember the dropout that Professor Huo talked about this morning? Well, you can have a dropout on attention as well, right? So dropout on attention will be just like generate a random mask and apply that random mask to your key query inner products. And that will potentially regularize the network, so you will get better generalization. There are other types of masks, right? Like there is windowed attention. If you have this becomes very much like convolution. If you have a temporal signal and you would like to only pay attention to the few elements before and few elements after, or maybe just simply few elements before, you can do that. Things like that are used in finance world if you want to do short time modeling of prediction of the market. So you don't want to look at the very large context. You would like to just limit yourself to narrow context. And then there are like other type of things like global attention, and then the combination of these is used in many different recent large foundational models. Like Big Bird that came in 2020 is using a combination of these three. Okay, so we have covered everything up to masked attention, and I promise that there is only one more thing that I want to tell you, and that is the cross attention. So what is the difference between self attention and cross attention? The only difference is that your queries, keys, and values are not all coming from the same X. Okay, so here, when we have an encoder-decoder architecture in a transformer model, remember there is a context vector. This context vector that's coming from our encoder is going to be behave as both the key and the value. So the key and value is coming from the context vector, but the query is coming from the decoder, the input to the decoder. So essentially, because simply we are decoupling, they are not coming from the same X, they're coming from two different entities. This is referred to as cross attention. Okay? And that's simple enough as well. Okay, so any questions on essentially multi-head attention or cross attention? Are we all good? Okay. So the next thing that we see in our block is this skip connection or residual connection. Okay. So it seems like the input is going to the output and being summed. So what is this? This connection is referred to as residual connection. And residual connection is actually a fundamental concept in deep learning. So let's start with convolutional neural networks that we covered this morning. You saw that the deeper, the better, right? In convolutional neural networks, it seems like LeNet started with, I think, like 3 layers, 4 layers, something like that. And then AlexNet had more layers, and then there's VGG's more layers. So that was the trend. Since 2012 to near 2015, the more compute you had and the larger your network was, the better you performed on the computer vision tasks. But then there came this paper, and you probably saw ResNet 152 in Professor Huo's presentation. This paper came that introduced ResNets. So it's a paper from Microsoft Asia. And they said, well, it seems like this trend is fine, but when you make it very deep, it doesn't work. So they showed that when they go and they generate, these are different convolutional layers. They create a very large model without residual connection the model that has a fewer number of layers perform better. This is the error. Y-axis is the error. X-axis is the training iterations. And you see that the blue is below the red. So that means like the deeper model is actually performing worse than the shallower model. And this was even true on the training set. So this is not just tests. You know, it's not, the problem is not overfitting. Overfitting is, of course, like, you know, when you overfit to your data, you can have a very large model that's overfitting to your data, and of course your performance is not good. But on training set, a very large model should give you perfect performance, right? Because it's very flexible. So here, even on training sets, the performance of a deeper model was worse than the performance of the shallow model. Then what is the culprit, like if that's the case? It turns out the culprit is the optimizer. You wouldn't be able to optimize these very deep models efficiently, right? Professor Huo talked about vanishing gradients. Like sigmoid has the issue that the gradients becomes smaller and smaller. Using ReLU will avoid that effect. So even if you are using ReLU, what will happen is that when you have so many layers, like the gradient information may explode and become very large, or may vanish and become very small, even though you are using like better activation functions, simply because you have so many of these operators, okay? And then this paper said, well, we have a very easy solution. Provide a highway for your gradient. Like your gradient, when you're doing backpropagation, you're calculating the gradient, and it needs to be calculated and multiplied by these matrices all the way to get here. So essentially, you will never be able, the signal is very strong at the end. The signal becomes very weak towards the input, okay? And to avoid that, you can generate this highway that allow your information to flow freely, your gradient information to flow freely and come all the way back, and you can optimize all the layers of the network. So this idea is, again, a very core idea, fundamental idea in convolutional neural networks. And this attention is all you need. Folks use this idea. So what this does, we have x1 to xn in our input. We have self-attention. I call the output of self-attention v1 to vn. We know how to calculate these now. Before I was calling them y. And then you simply bring these x's and sum them with the v's. So I now have z1 is equal to x1 plus v1 and so on. Okay, that's that skip connection, that residual connection that we have. And these will allow us to train the models much more efficiently. Okay. But when we are using residual connections, so now we want to go to the next layer and talk about what is this normalization. Layer norm is layer normalization. Why do we need layer normalization? Even in the ResNet paper, in the residual convolutional neural network paper, the author said, like, hey, when we add this residual connection, we are essentially saying that the updated feature is the previous feature plus some computational block applied to the same XT. This is exactly a residual connection. By the way, for those of you who are interested, this can be thought about as a discretization of an ODE, or and that's what referred to as neural ODE, but that's for another time. So because this F can become large, we are accumulating things over and over. So again, these can become numerically unstable very fast, right? So to avoid this numerical instability and allow for good optimization, we need to do some sort of a normalization. So we actually go and we normalize these FTs. So we normalize these XTs, and then like when we are updating things, we sure that we remain mean 0, standard deviation 1, right? So every layer is going to remain in the same kind of same range of values, okay? So in convolutional residual neural networks, or ResNets, this normalization was batch norm, and in transformers, people switched it to layer normalization, and you will see that these two are actually very similar. Just for the reference, batch normalization was a paper from Christian Zaghetti. He's at XAI right now. He's, I think, the chief scientist there. And this paper is cited 61,000 times since, I believe, 2015. And this layer normalization is a paper from Jeff Hinton's group, again, another AI godfather and the Nobel Prize winner. And that was a more recent paper, 2016, and that one is also cited 14,700 times. Okay. So these normalizations, the reason the citations are high because people use these normalization in their work and they show that it works, right? Like it's a very practical idea. That's why there's so much citations on this paper. But what do they do? Let's start with batch normalization. Let's assume that I have a batch with n elements and each one is d-dimensional. So I have n vectors, each one is d-dimensional. What batch normalization does, it says that this d-dimension, each one of them is a feature 1 to feature d, right? And I have those features for different elements. I go and I normalize, I apply a standard scalar on each feature. And what is the standard scalar? I simply go and calculate the mean of that feature. And then I calculate the standard deviation of that feature. And I do the subtract the mean, divide by a standard deviation. Of course, if the standard deviation was 0, you don't want to get numerical instability. So you add a small epsilon there to be careful. Okay, so what this does is that it will simply normalize each dimension of your feature space. And then it brings it and makes it mean 0, standard deviation 1. And then you can simply shift it to where you want with variable beta and scale it with however scale you want with variable lambda. So this lambda and beta become learnable parameters for the batch normalization. Okay. So this, again, is a very useful normalization, but there is a problem. And the problem is that this depends highly on your batch size. Like how big or how small is your batch size is going to affect your performance a lot. So what layer normalization does, it says you do the normalization very much similar to what we had here, but instead of calculating the means for each feature, you calculate the mean of all features for the same x. So if you look at it, like I have this mu I defined as the average of the values of this vector, right? So I do a mean that way, and I calculate the standard deviation. This is akin to moving things on similar to moving things on a sphere. It's not exactly moving things on a sphere, but it's bringing things and normalizing things that way. And still, we have the lambda and beta here, which are your learnable parameters. So again, the only difference here is that instead of calculating the mean across features in batch normalization, in layer normalization, you do this for one sample, and you calculate the mean for that that entire vector that you have. Okay. So any question on what's batch normalization, what's layer normalization? Okay. Now, we have covered our transformer block up to here. What remains is only these MLPs, right? Like, because we have another skip connection and another layer normalization, we know how to do those. So what are these MLPs that we have? We know that multi-layer perceptrons, I mean, again, Professor Huo talked about this. Multi-layer perceptrons are very powerful computational units. They actually, if you have a multi-layer perceptron with one hidden layer, you can show that that's a universal function approximator given that you have enough neurons in your hidden layer. What I mean by that is that you can simply think your activation is something like a sigmoid or a step function. And if I have two of these step functions, I can create a bin. And then if I have a function that I'm trying to approximate, all I need to do is to provide the different bins to approximate this function. And each bin comes with 2 neurons. So if I have enough neurons, I will be able to cover this function. And if I want to cover this function more accurately, I just need to make these bins narrower and narrower. And that means I will need more and more hidden layers. So this is a kind of a depiction of a proof for universal approximation theorem that says a multi-layer perceptron with one hidden layer can approximate any continuous function. Okay. So now, like when we train these models, what will happen is, of course, like you have some data, you have some model, and then so your model is your multi-layer perceptron, and you have some objective, in this case, let's say mean squared error, and you probably saw something very similar to this yesterday, where you do gradient descent optimization of your model parameters, and it fits the function nicely. And I just want to say that actually there is information, and there you can explain and see what the network has learned by looking at the activation of the hidden layers. The hidden layer that you have, I call these phi m's. And you calculate the output is simply a linear combination of these hidden layers. And you see that after I train the network, these hidden layers are going to look like these nonlinear functions. And I'm calculating a linear combination of these nonlinear functions to create this red curve, right? So the same thing happens if you do, for example, classification. Again, universal approximation theorem that tells you that you can approximate any function that you want with such multi-layer perceptrons. What are these? Linearity, nonlinearity, and other linearity. That's a linear function, exactly what I wrote before. I have something that looks like this. Y is equal to W2 sigma W1 X. This is what you have here in the middle. And the last W is what generates the weights for your final neuron. Okay, so this shared MLP is essentially going to apply the same MLP to the individual tokens that we have. That's all. So, and this shared MLP is usually just has one hidden layer. Here, what I'm depicting has two hidden layers. You have control over, but in the original paper, you only had one hidden layer in this MLP. So you should really think about it as a nonlinear transformation of your tokens. This is PyTorch and Python and PyTorch. Yeah. So yes, we had our MLP here. We apply the MLP to the individual. So if we have all these layers, we have the layer normalization. We generate this output. We send this output to the MLP. We get the output. We have another residual connection, and then we are here right now. Okay. So we should really think about it as this. Here, I have an all-to-all communication between my tokens with some nonlinearity. Here is where I actually nonlinearly transform my tokens the most. These MLPs are going to nonlinearly do the nonlinear transformation for me. And then, of course, if I apply this again, I'm going to do another all-to-all computation and another nonlinearity. Okay, so to put everything together, self-attention, residual connection, layer normalization, MLPs, and a final layer normalization, and that's your entire transformer block. Okay. So, and this is now, if I go back to what I had before and show you this, now we just created this block, this brick. These different colors were the different components that become. So now you need to essentially put these together to be able to generate something bigger. And for us to be able to do that, we simply compose these transformer blocks together, like that. So I have the input tokens, transformer block 1, the output tokens. Remember, this whole operator is a set neural network that's permutation equivariant. I apply another composite with another transformer block, I get the outputs. And if we look at the original paper, what it said was they have n of these elements. So the beautiful thing is that since 2017, this architecture has not changed much. Okay? It's more or less exactly the same thing that you're seeing here, all the transformer networks, with one minor change. And the change comes from this paper that says, it really matters where you put your layer normalization. The original paper said the layer normalization must be done after the attention. And these authors questioned that design choice and said, like, let's see what will happen if we put layer normalization before multi-head attention. They actually have theoretical reason behind why they proposed this. And they showed that in a lot of different applications, when you put the layer normalization before attention, it performs better. That's the only change since 2017. Okay, so while we see this, we know that today, when we are talking about transformer blocks, these blocks must be moved back like these layer normalizations must be moved before attention and before the ML. And that's the only change. Okay, So I think like we are at, it's 3, so we take a break now. And when we come back, I'll talk about tokenization and we jump to actually code the transformer block.
Just kick something, sorry. I've been asked to make an announcement about the slides and that sort of thing. We will be posting slides. We're not sure whether it's going to be in a Dropbox or on a website. We will let you know as soon as we figure it out. We have taken videos. We're not sure how they're going to turn out. Those will be posted if they're worthwhile at some point in time. And I want to thank everybody for being here. I'm sorry. Oh, yes, I'm sorry. That was why I kept looking at Dr. Seckman. Also, we're going to send a post-event survey within the next day or two. We'd really appreciate it if you could answer that. It lets us know what we did right and what we did wrong and what we should do next time. Thank you very much.
Okay, last stretch. Okay, good. We talked about the transformer block, and then we said that we are going to compose all of these to create essentially large, deep neural network or a transformer model. But now I want to focus a little bit on the input that we send to these models. Like like the inputs where I said that there is a set of vectors. What are these set of vectors that we send in these models? Okay, so. And that's the topic of tokenization and positional encoding. You know, if what you send in these neural networks, it really depends on what the application is. Okay, and that's the beauty of it. So long as you can shatter your whatever type of input that you have into vectors, a set of vectors, you can use a transformer, and that's why they are universal. They are used in many different applications. For example, when we have text, this movie is great. You can simply tokenize these words. Let's say each word is represented with a vector. In the natural language processing community, this problem has been studied for a very long time with different word embeddings and so on. So, but like at the end of the day, each word is going to become a vector. And then these vectors are going to go to your transformer network to do whatever you want to do. If you want to do, for example, text generation like GPT does, or you want to do sentiment analysis. Was this a good review of the movie? In fact, I have the code for sentiment analysis available, and we will review that. Okay, so, and the idea is that this word embedding space needs to be in a way that it's actually semantically meaningful. So we would ideally like the tokenizer of, like, let's say king minus tokenizer of male be the same as the tokenizer of the queen, right? Like, so there should be some sort of a semantic meaning in that. When we are talking about images, well, like we can break an image into pieces as well, right? And if I break an image into these patches, I can simply tokenize each patch. This tokenizer is a function that gets a patch, gives you a vector, and then those vectors are going to go in my neural network. Okay. Tech, speech, and other domains, a very similar way you can tokenize them. But so let's look at, for example, in tokenization for large language models. The most common way of doing this these days is byte pair encoding, BPE tokenization, which is a subword level tokenization. So you essentially would like to break a word into pieces, and these pieces are going to be mapped to an integer, right? It's to an index. So you have a dictionary of pieces of words, and this dictionary is huge, right? And for each piece of word that you have, you know exactly what is the index in that dictionary. And that's going to be the tokenization process. So you go from a word into pieces of the word, and for each one you have an index. How does this happen? This BPE uses some sort of a clustering, essentially. It looks at the frequency of different pairs happening on a large corpus of data. So here I'm showing a DNA sequencing type data. So these are the different the ATGC of a DNA, And then you have like, you see that TA is happening like 3 times here. Of course, the core vocabulary that you start in first step is like just the characters, and then like you start adding by clustering things that happen frequently. So that's how it works in practice. But this question actually came up during the break as well. Like what other options you have? You can use many different types of tokenizers, and some of like this shows what is used for the different models. Of course, a lot of these we just are kind of guessing what is exactly used, because these models are black box. The companies are not telling us exactly what it is. But so GPT-4, for example, is using a newer variant of the byte level BP, which is byte level BP is an advanced way of BP and so on. But nevertheless, you have a way of shattering your input into tokens. Okay, but here is points that I kind of emphasized on several times, that these transformer blocks are permutation equivariant. And there is a problem here. So what is the meaning of permutation equivariant? If you permute the input, the output will get permuted. But we know that there is a different meaning, whether we are in text or images. These texts, the dog chased the cat or the cat chased the dog, are very like different things. They mean very different things. And because we are talking about set neural networks, they are going to be processed exactly the same because they are a permutation of each other. Okay, so here we have a problem. This permutation equivariance in transformer networks could be very limiting, and because order matters. So there is an easy solution to this problem, and this brings us to the idea of positional encoding. So all that it says is that, yes, you have these tokens for your word, but you don't necessarily know exactly what location they're coming from, because this is a set, right? One thing you can do is you can encode the position into a vector and add it to the words, okay? So I can say, essentially, I have a 3-dimensional vector that says this is location 1, location 2, location 3, location 4, and I add these vectors to my words. So now, even though this network remains to be permutation equivariant, but if I permute the input words, my output is not going to be permuted. Why? Because the addition of like the location have not changed. If I permuted everything, my output will be permuted as well. But because these locations are fixed and not permuted, then this becomes a not permutation equivariant model with respect to the input sequence, with respect to the input words. Okay, so this is the idea. Now the question is, what should this d-dimensional position embedding be? So I have d-dimensional token vectors. I need to add these positions to it. What should those be? Well, let's start with something simple. If I had only 16 positions, I can use 4 bits to encode the position. Okay, a 4-dimensional vector to encode those positions. But if I put all of these together and I look at them as essentially a signal, the first location, second, so on, I see that if I visualize these, there seems to be a kind of a harmonic thing happening here, increased frequency of a pulse happening here, right? So I have low frequency, higher frequency, higher frequency, and higher frequency. So here I had 0 and 1s, but I can essentially get inspired by this idea that it seems like something that encodes frequencies would allow me to embed position. And instead of binary codes, I can use sines and cosines with different frequencies. Okay, so now instead of 0 and 1s, I'm going to have actually continuous values. Okay. So this is from the original paper, Attention is All You Need. It says that let's create this position vector. T is the location. Let's say we would like to get the position vector at position T of our input. So I have sine of omega 1t, sine of omega 1, cosine of omega 1t, all the way to sine of omega d over 2d t, cosine of omega d over 2t. So I wanted a d-dimensional vector. I broke my d into 2 pieces, and I put sines and cosines essentially with different frequencies. Now, what is this omega? This omega in that paper was set to 1 over 10,000 to the power 2 kd. Why? Because they wanted to essentially obtain a log scale sampling of the frequency space between 1 and 10 to the negative 4. Okay, and that would allow them, in the paper they say this will allow them to model short-term and long-term positional patterns. But for the sake of our discussion, all we need to care about is that I can use a bunch of sines and cosines to encode the position information. For those of you who are interested in knowing exactly where this comes from, I put the references. In fact, the core idea comes from a paper from Rahimi and Recht in 2007, which won the Test of Time Award at NeurIPS in 2017. And it has something to do with the Bochner theorem and the Fourier transform of, representation of shift invariant positive definite kernels and its relationship with Fourier transform. But I don't want to bore you because I think like I was reminded in the break that, okay, like we need to cover more broad concepts, not too much detail of mathematics concepts. So here, let's skip over this. For those of you who are interested, the information is there. You can, when the slides become available, you can access them. Okay, so those positional encoding that we talked about are actually from the original paper, and they simply used sines and cosines with fixed frequencies. And you can immediately imagine that the community doesn't just sit and use that. They try different types of positional encoding and see how they perform. So one easy idea is that why fixed sampling of the frequency domain? Why don't we actually learn what frequencies are going to be more important for a specific application? Why don't we make those omegas that we were seeing in the previous slides learnable? So that's a learnable positional encoding idea, and this has been done in the literature. More recently, and this is kind of chronological, that was the first idea after the original paper. The second idea came and said, well, maybe the exact location is not as important as the relative location of these different tokens. And that makes a lot of sense if you have a moving context. This context window can be very large, but nevertheless, you can't have infinite context because of the quadratic attention, or even linear attention is going to become very slow. So you need to do some sort of a relative position of different tokens. And that means, for example, instead of saying this token is at position 172, it says this token is 5 steps ahead of another token. Okay, and this helps the performance significantly. And more recently, the GPT models, Palm, ChatGPT, Claude, and all of those use another method called rotary positional encoding, ROPE. And what they do is they rotate the queries and keys depending on the location that you have. And it turns out that when you calculate the attention, then that becomes a relative attention. Okay. Okay. We don't necessarily, again, need to go too much in the details of how that is done. Okay, so any questions on positional encoding? Your network is permutation equivariant. That's bad for a lot of applications. You add the information about the location of tokens so it can differentiate, understand cat chasing dog versus dog chasing cat. That's all. Okay, so now I want to put this all together and let me actually do this one time with the quickly with the NLP application, and then I do the VIT application in the computer vision community as well. So let me put this, and then I write something in my notes. Let's have this architecture in mind. So we have all the elements of this architecture, learned all the elements of this architecture. We have some input. We have an input embedding, which is our tokenizer. We have a positional encoding, which we just saw, it's those sinusoidals or something like that. And then it goes into a transformer block. This is an encoder block. And what comes out of this encoder block is a context. Okay. And this context goes into a decoder, and this decoder gets some its own input that's coming from the output. And okay, it has self-attention, cross-attention, and everything there. But like, I want to give you an example of how exactly this works so you get a sense of what happens in this architecture. So if I go to my notes, I can, let's think about an LLM, a large language model. So what I can send in this large language model is write an essay about transformers. Okay, so what's going to happen is this, each one of these words is going to go into a tokenizer. And we get a vector. So let's say I get a vector per element. And then what will happen next is that I will bring a positional vector. So I will bring P1, P2. These are the simply positional vectors. And I add these positional vectors to this up to PT. I don't know how many words I had. So what are these? These are the position vectors. Okay. And at this point, I have my x's. This is what we were calling x before, x1 all the way to xt. So these are my input tokens, okay? Which have the position encoding. So this goes into a transformer layer, transformer block, which we know exactly what it is. And what do we get in the output? We get some, let's say, I don't know, x12, x22, xt2. An updated message passing happens and multi-layer perceptrons happen, so these features get updated. Okay. Still, all of these are d-dimensional. These are all d-dimensional as well. So do I have one transformer block? No, I have multiple transformer blocks. So I will have a bunch of these transformer blocks, dot, dot, dot. And I come out up all the way here. And I simply, instead of writing XL, I call this Z for simplicity. Z1, Z2, ZT. So what is Z1 in this example that I'm writing? Z1 is going to tell me something about writing. It corresponds to the word write. But it also has all the context of this sentence because I have been using all these message passing between these vectors. So it knows that it needs to write. Z1 encodes information about writing. It knows about essay, and it knows about transformers. Okay, so now Z1 has that information. How about ZT, transformers? So it knows what a transformer, like it essentially says, this is going to be what this Z is about. It's a transformer. In what context? In the context of writing an essay, right? So these Z's encode all those information. So now let me just put all of these Z's into a single, bring this information into my decoder, and you will see what I want to do. Now I want to tell you like how these models actually work. Like how do we generate text? So far we cannot necessarily generate text. So we start by a token called a start. Okay, so we know that this token is the input to our decoder, and that's essentially telling us that you need to start writing. This goes again in a tokenizer, positional encoding added to it. It goes through a decoder block, which has a self-attention. And then remember, it has a cross-attention. So this self-attention, what is it doing? The self-attention is telling us what have we generated so far. It's at the first iteration is not interesting because we haven't generated anything. It's just a start. It pays attention to itself. I need to start, right? But the start what? Then it comes in and says, now I have cross-attention. So now it says I need to start an essay. Like if the attention is going to go on all those Z's, and it's going to be a start an essay. It's going to pay attention to essay. And then essay about what? Pay attention to the transformer, right? So then what will it do is I generate, I think for the lack of a better thing, I simply use V here. I have V1. I said U1 at this point. I generate V1, and then I have a bunch of these layers, like n of these layers. And at the end, I get one vector. Let's call it S1. This is simply n of these decoder layers that is trying to understand what needs to be said. At the end, I get simply a vector out, which was an updated vector for my input U1. And this vector is going to go in a linear classifier. So what is the output of the linear classifier? How many classes do we have? We have as many classes as the number of dictionary tokens. So say we were actually trying to encode every word in the dictionary to an integer. How many words do we have in English? I don't know, 100 something thousand, whatever, right? Let's say we have 125,000. Then the output of that linear classifier is going to be a 125,000 dimensional vector. Okay? And then what is it doing? It's a softmax, it's a soft label, so it has a probability distribution on what should be the word. Okay? So here I get a probability distribution. Let's say in this probability distribution, the word transformer, the word neural, and blah, blah, they're all the words in the dictionary. And the probability distribution that I'm generating has low values here, maybe a high value on transformer, maybe a high value in the neural, and a bunch of others. And then I can sample from that distribution. And let's say when I do that, it generates the word transformers. Okay, so what do I do next? I take this, I come back, I tokenize it, and then I have U2. I do the positional encoding. Now I have U1 and U2. That goes in. I have V2, goes in a bunch of other things, and I have S2 in the output, S1 and S2 in the output. Then I send that linear classifier. So it knows that what it has said, it knows what is the context always. It knows exactly what is the context when it's generating everything. And based on the next word, it tries to predict what is the next word after that. Okay. And then, for example, it will be transformers are, and then transformers are comes in and goes in again, and there's one word at a time, one word at a time. You do many, many iterations, and then until you reach a point called end of token, end of I'm not sure exactly what is the last character for it, but let's just simply call it end of token, but end of sentence or something, EOS. And at that point, it stops. It doesn't do the forward pass anymore. Okay, so this is how your large language model is working. This is how ChatGPT is working, right? Now, like exactly how many neurons are they using and how many transformer blocks and transformer encoders and decoders are using, we don't exactly know. But at least we know that there is this encoder-decoder architecture in this model. Okay, so this was for text. Sorry. And now I want to quickly go and tell you that the same idea can be applied to vision. And this brings us, instead of convolutional neural network, to vision transformers. Okay, so how can we tokenize an image? Well, the easiest thing for an image, which would be equivalent of tokenizing characters in a text, would be to tokenize the RGB value of each pixel. Map each pixel RGB values into a vector. But there's a problem there. The number of tokens grows because your image can have many, many pixels, right? And we saw that if the number of tokens grow, it's quadratic, the quadratic attention is going to essentially make things too slow. So instead of doing that, we break the image into patches. And then we send these patches into simply a linear function. We flatten them, we send them into a linear function, into a d-dimensional vector. And then we add our positional encoding and we send them through the transformer to generate output vectors. So there is a slight difference here between what we were doing in the natural language processing autoencoder and what we need to do for the transformer. If we want to classify this image as a cat, then I need one feature to represent the image. Remember, these transformers will give me a set of features. Okay. The question is, how do we generate one feature? There are many ways to do this, but the vision transformer paper said we are actually going to add another learnable parameter. Let me point to it here. And we are going to call this the CLS token or simply the classification token. This is referred to as the CLS token. Okay. And then this is a learnable parameter, d-dimensional learnable parameter. And of course, I'm going to have an update for that feature. This feature is going to talk with everyone and update its information based on the information of all other tokens, as we saw, through self-attention. And then I will have one of these transformer or multiple blocks. Of course, I will have multiple blocks of this transformer. I have n of them. And then at the end, I have all these features, but the only one that I use is the CLS token feature and send that into a classifier, a linear classifier, with the however number of classes that you have. Okay? And this will generate your vision transformer, VIT. Okay, so yes. Yeah. So there will be okay, so each point is going to be an X. So when you're doing self-attention, you're paying attention to all other pieces, right? Cross-attention is called cross-attention because the keys and values are coming from another domain, something else. Here, everything is within the same domain, right? But that's a good question for a different type of model. If I wanted to have a model that integrates text and vision, then I can use something like that as cross-attention. Like bring the information from text and then an image and do a cross-attention. Yeah, here everything is actually pure attention. Okay. Does it make sense now? How this model works? Okay. So for the rest of the session, what I'm going to do now is try to switch and start coding in PyTorch. Okay. So okay. So if you have your laptops with you, you can go to my GitHub account. It's Kolouri. So you see it up here. And the repo is called Tiny Transformer. I have the link to it in the presentation as well. So simply, if you go GitHub, Kolouri, Tiny Transformer, you will land on this page. And here, you have a README that you will understand exactly what this is. But let's click on this IPython notebook. And what we're going to do is we're going to open this in Colab. Okay. And now you will have access to this code. Okay. So that's okay, right? Okay. So I don't know, again, how much we are familiar with Python or PyTorch, but so I try to keep it intuitive. I have written it into blocks. So let me break all these into the high-level picture first. So in this Colab or IPython notebook file, what I've done is I've created a minimal transformer which shows what's an encoder, what's a decoder, does build different blocks of the transformer which we saw together. And then it goes and shows an application of the transformer in Vision. It performs, creates a VIT and applies it to MNIST and shows performance of a tiny VIT on MNIST. Then it does an NLP example of sentiment analysis. So we create another network to analyze text and do a classification on sentiment analysis for movies, right? And then lastly, we do an encoder-decoder training on Shakespeare. So just a heads up that the first two actually run very fast on GPU, but the last one is going to take a long time and it requires some computation. So what I'm going to do is I'm going to go through the first two. The third one, I will just show you the results after training for 5 epochs, which generates something, but it's not perfect. Okay, so of course, you need to kind of load some libraries, and the library that we use extensively for deep learning is PyTorch. So again, I'm not going to go line by line, but I try to at least keep things at the conceptual level. So positional encoding, remember what this was. Positional encoding was a bunch of sines and cosines, and it said it provides a d-dimensional vector with these sines and cosines. So I create a class for positional encodings, and I tell it what is the dimension that I want my vectors to be. What is the dimensionality of those vectors? And then I say, like, what is the maximum length that I would like to be able to encode? That maximum length is the 16 number that we had in our, what's the budget? How many words will you want to encode? And here I set the default to be 5,000. It can be anything else, depending on the application that you have. So what we do is we create this positional encoding vector. We fill it with all zeros. And then if you look at it, we create some, the frequency terms. And then we simply go and say, fill this positional encoding with a bunch of sines and cosines with the corresponding frequencies, right? And then when we do a forward on this positional encoding, this is when it applies this layer on the tokens. And you can immediately see what it does. It simply adds the positional encodings to the input X. So X's are, let's say, the patches of image that came. And then this positional encoding is the position of those patches. And if I go and I visualize these are, again, a bunch of sines and cosines. And so you see this positional encoding matrix that are the different frequencies that we were looking at, but in a continuous form, not in a discrete, not in a binary form 0, 1 that we saw. Okay, so this is positional encoding. I would say like one of the least important parts of the network. Let me turn on the GPU, and then so we actually run the code as we speak. So yes, yeah, and this is on Colab, so you can run it on Google Colab for free, and exactly should run, like you should have access to this. Yeah, yeah. So I mentioned where this code is. This code is on here. Kolouri tiny transformer. Should I send it in chat? Yeah, that's a good idea. Okay. Okay. So we just generate. I believe we just generate. Oh, this is it. Okay, we just generated that, so the code is active. Next, I'm going to go and define the next thing that we saw, which was multi-head attention. Again, I don't want to bore you with too much detail, but let's look at the important things. Here, we would like the, what do we want to have? We would like to have the dimensionality of the encoding, the dimensionality of our tokens is the important thing, and the number of heads that we are going to use, okay? So we get those as inputs for initialization. Then we calculate this dk, which is going to be our key dimension. And remember that we broke the d into the number of heads because we want to concatenate all of these together. All of the outputs of the heads are going to come out and be concatenated into a d-dimensional vector for us, right? So we break the d model into the number of heads and call that the key dimension. And then what we do is we go and we create our query, key, value matrices, D model, D model, D model, D model, all of them. And then this is the last linear layer that we had after concatenation. If you remember when we talked about or multi-head attention, we had these different heads and we concatenated their output. And after the concatenation, we applied a linear layer. Okay, that will do that. So when we do a forward transfer, we create the QKV. You may say like this is generated for the entire thing, not per head. But what we will do is actually we go and we just simply break these. We generate this one time and then we break them into the query and keys for different heads. And go and calculate our attention. And if you remember, we had QK transpose divided by the square root of DK. So that's the scale dot product. Do we need a mask? In this application, I don't need a mask. I have like, if I needed a mask, I apply the mask to it. I fill it with zeros. And whenever I have 0 in my mask, I apply a negative infinity. So it receives a binary mask, and then it fills the zeros with negative infinity. And we saw why we need negative infinity, because when you apply softmax, it becomes 0. And and then at the end, you calculate your attention based on the softmax on the scores, and then you do the multiplication of your attention and the V. You get your output. And then here we need to concatenate all the heads back. So that's what we do here. Concatenate attention heads and run through the final fully connected layer. So here we concatenate, and at the end, we send it through another fully connected layer. So what are the learnable parameters? The WQ, WK, WV for all heads, and this linear layer that we have at the end are the learnable parameters for the multi-head attention. And of course, I have the test to ensure that every layer is implemented correctly, and the inputs and outputs match, and so on. Okay, so we have positional encoding, we have multi-head attention, we need multi-layer perceptron, those shared multi-layer perceptrons. And layer normalization is already implemented in PyTorch, so I don't need to bother doing it, right? So we will just use the pre-trained one. So here is my feed-forward network, simply a multi-layer perceptron with a single hidden layer with D underline FF number of neurons in the hidden layer, and it gets that as input. It receives the information about the dimensionality of the tokens, the dimensionality of the hidden layer, and the dropout rate. Again, what is dropout? Randomly drop neurons in your neural network to make it more generalizable. So we talked about it in the morning section. Professor Hu talked about it in the morning session. So here is our multi-layer perceptron. Has a linear layer that goes from D model to DFF. It applies, and that's here. It applies a ReLU and nonlinearity. It does dropout on top of it, and then it applies our second linear layer, which goes from DFF to D model. Okay, so this is the one hidden layer MLP. And again, like there is a quick test that you can check to see if it works. Let me just quickly run these so our code is up to date. Okay. Now we have everything that we need to go and define our transformer block. Okay. I call this transformer block simply a transformer encoder layer because it doesn't have the cross attention. If I want to define the transformer layer for the decoder, I call it transformer decoder layer, and then I put the cross attention there. So here, again, like let's look at the forward very fast. What we have is X as input and the mask. The X goes into a multi-head attention. The XXX is going to be the query key and value. Those matrices are going to be applied to these. The reason we have written it this way is because it makes cross attention easier. If you want to write the cross attention, the coding is going to become much easier. And it gets the mask. Then you do the dropout on this attention, multi-head attention, and then add it to your X. So the dropout, again, in the original attention is all you need paper, is added in every layer of a transformer. Then we do the normalization, layer normalization. After that, we send it through the shared MLP, do another residual connection with dropout, do another normalization. And notice that here we are using the original attention is all you need. The norm layer is after attention. And we said that's actually not the best practice. You should bring it before attention. But I wanted to remain close to the original paper. Okay. And so this will give you your encoder layer, which if you want to have an autoencoder, you will need to use. And then we have a decoder layer. And if you notice in the decoder layer, the only thing that that's different is that we have self-attention. And then we have this cross-attention, which gets X, and the encoder output and encoder output. Keys and values are coming from the encoder. The query is coming from X, the decoder input. And everything else is essentially similar. And this you can go and map it to the exact figure that we had in the presentation. Okay, so now I put the decoder layer there too. What if I want to generate a causal mask for different application? I define a class for that as well, and I say get the sequence length and simply generate an upper triangular, a lower triangular matrix for the causal attention. Remember, this was for the case that I wanted each token to only pay attention to the previous tokens. Okay, so we generate that. Okay. Now, let's go and stack some encoder and decoder layers. So if I want to generate a transformer encoder, I will need multiple of these transformer encoder blocks. I need to compose them together. So if you see here, I go and define my layers to be a neural network module list of the transformer encoder layers. And how many of them do I need? The number of layers is an input. So however number of layers you want, it will essentially generate as many of those transformer blocks for you. Okay. If you remember in the image, we had times n, transformer block times n. That n is your number of layers, and this is exactly that transformer layer times n. Okay. And when you do the forward transform, of course, it's fairly simple. All you need to do is to send the input through the different layers and compose them together. So X gets updated by being sent through these layers in a for loop. Okay. And similarly for transformer decoder, we can essentially go and do the same thing and decode, put a lot of these decoder layers together. Importantly, when we do the forward pass on this layer, transformer decoder needs to get its own output as well as the encoder output, which is the context that we talked about. So here, I run some dummy tests to, again, just ensure that my model is, the model's, the input outputs, at least the sizes match, a very fast test, unit test to ensure that. And at the end, if I want to put a full transformer autoencoder together, I call this the transformer model. And then I will need to have some tokenization, calculate the embedding depending on what is the vocabulary side and what is the dimensionality of my model that I'm going to consider. I will have the positional encoding, then I will have my encoder, and I will have my decoder. And this generator is that classifier that I talked about that you need to put at the end of your decoder layer, right? Remember that S1 came, I think I wrote it somewhere, it's in my notes. S1 came out and went into a classifier that generated the probability over all the words in your dictionary. That's this final classifier, the generator. Okay. And in your forward, of course, you embed your input, you multiply it by a square root of d, again, for simple normalization. You send it through the encoder, you get your encoded output. You do the positional encoding, you send it through your encoder, get your encoder output. And after that, you do the same thing for the output, so the input to the decoder, and then you send that through the model to get the decoder output. Of course, you can notice that the decoder gets the encoded target, which is like its own input, as well as the encoder output, which comes from the encoder. Okay, so I'm going to skip over this. This, I think, is just there for completion. Like, I would like us to be able to model a full transformer, but let's see, now that we have all the blocks, let me give you a live training example of how to implement a vision transformer based on these building blocks that we have. Okay, and hopefully I'll have enough time for everything. So now, the VIT model that we had, we said that it's going to get patches of images and then project those patches into a vector, okay? So what is the size of my image? I'm going to apply this to MNIST. So MNIST is 28 by 28. I'm going to make 7 by 7 patches and break my image into, yeah. Oh, sounds good. So MNIST is the handwritten digit recognition example that we were seeing this morning. So it's simply that different digits like 0, 1, 2, so on to 9, This is the handwritten digit recognition data set. Each one of these images is a 28 by 28 pixel, and they are grayscale images. Okay, so that's what we have. And what we are going to do is we are going to break these images into 4 by 4 patches. Each of these patches, the size is going to be 7 by 7. Okay, we are going to vectorize these, send them through a linear layer, and that's going to generate, that's going to be your tokenizer. That's going to be your tokens that are going to be input to the model. Okay, so here you may see something that's actually a little bit interesting. I'm using a conv2D that goes from input channels, which was 1. You saw this earlier this morning. I have the dimension of my model, the dimension of my tokens that I would like to have in the output, but my kernel size is exactly the patch size. It's 7 by 7. What is this convolutional neural, like this conv2D, what is it doing? The size of your image and the size of your convolutional kernel is the same. It's simply a linear layer. It's as if you have flattened your image and multiplied, like calculated linear function on top of it, right? So essentially, it's not doing really convolution. It's simply a linear layer applied to your patch. So this conv2D is a little bit of a I would say tricky thing, because it's actually not doing convolution. It's simply doing a flattening and a linear layer. But because we are too lazy to flatten and do it, you can simply use conv2D and it will do the same thing for you. Okay. Of course, I mentioned that we have a learnable classification token. This is the CLS token. This CLS token is going to be D-model dimensional. The reason these two one-on-ones are there is because I want to essentially concatenate it to the rest of my tokens and send it into the model. But at the end of the day, it's simply a D-model dimensional vector. Okay, so here in this VIT, we are actually going to do something different from the sinusoidal encoding, and we are going to let the positional embeddings be learnable parameters. I told you that you can make these learnable parameters. Those P vectors that we have for each position can be a learnable parameter, and that's exactly what we're doing here. We created a number of parameters, number of patches, 1 plus number of patches times D model. Why 1? Because you have this CLS token that's also added, and you need to have a different token for different position for that CLS token. And the number of patches is going to be 16. Okay. Great. So we have dropout. And now all we need to do is to create some encoder layers, because VIT doesn't have a decoder. It's simply a bunch of decoder layers. So a bunch of encoder layers. So I have an encoder layer, transformer encoder layer. The D model is the input and the number of heads. We talked about DFF is the size of the hidden layer of the MLP, and I have my dropout. I have number of layers. So however number of layers that I want to add these, I give that as an input. And of course, like I need to have layer normalization. And at the end, the linear classifier is going to have get the CLS token and predict the class for me. So when we call the forward on this neural network, it's going to get the batch size, and then go and do the projection for us. This is simply that convolutional 2D that we had. Flatten the spatial dimensions and then transpose it, so we get the B number of patches D model. We add the CLS token. We concatenate the CLS token to our tokens from our images. We add positional encoding. We do dropout. We add our transformer layers. We normalize the output of the last transformer layer. Get the CLS token in the output. Send it through your classifier. Get your logits. Logits are remember, like we said, like when we have a classifier, we would like to predict a distribution over our different classes, class 1, class 2, class 3, all the way to class K. So I would like to generate a distribution over these. So what will happen is at the end of the network, let's say we have some UIs corresponding to the logits of the different layers. These come from some WXI, okay? oh, sorry, WX. So what will happen is that you would like to create a, this is the ith element of that. You would like to create a probability distribution for that. So you simply send this into a softmax, which we saw that it's E of UI divided by sum over J of E of UJs. So this is probability I. And here, let's say that's probability for class 1, probability for class 2, probability for class 3, all the way to probability for class K. Okay. So these U's are referred to as logits. Logits are the output of your network before you turn them into a probability vector. Okay. So long story short, based on the logits, you can predict the class of your class. You can simply look at the maximum logit value, and that will give you the maximum probability. Okay. So we do that. So now we have our VIT model. We get the data. So it's downloading the training set and the test set. Maybe I actually visualize some of this data so so we look at it. On Colab, right now, actually, we are not using the GPU, but I'll be using GPU for the training. Because so far, we haven't trained or do any inference on the model. Let me run this again. I think like maybe there's an internet issue. Oh, good. It's completed. So let's simply look at one of these images. Let me see what is the size of my trained data set. Okay. So I'm going to do this. Okay, and let's look at this. So these are the handwritten digits that we were talking about. So digit 5, for example, right? So, and of course, there is a corresponding label for it. So we have 60,000, our training set for MNIST has 60,000 handwritten digits with their labels as training set, and 10,000 handwritten digits with their labels for the test set, okay? So now, what we do is, in this is an important block. We instantiate our model. We say that our model is a VIT. Remember, data, model, loss, optimizer, okay? But data is MNIST. Our model, we have already defined it, is the VIT. So we instantiate the VIT. I say my image size is 28, patch size is 7, blah, blah. The number of input channels is this, and so on. So I have all the information that I want for my VIT there. I actually print my model, and my model is, even though it's a fairly simple VIT, you can see that it's already pretty involved, even though it's very simple. Then I have to say, what is I have my data and my model. What is my loss? I'm going to use the cross entropy loss. Again, this is not an ML class, but cross entropy loss would be equivalent to the negative log likelihood solution for the classification problem, okay? And so that's the loss that we usually use for classification problems. I call that the criterion. And then I have an optimizer. In this case, I'm going to use Adam. Adam is just a variation of gradient descent, okay? It has momentum added to the gradient descent, okay, at a high level. So but that's simply saying that I am going to use some sort of an accelerated gradient descent on the model parameters that I have to minimize my loss function, okay? And I do that. Okay, so now we need to do the actual training. So I have all the components. I need to do my gradient descent. I think it's important for this we go line by line. What is an epoch when we are training a neural network? An epoch is whenever you see your entire data set once is one epoch, okay? I'm going to say I would like to train my model by seeing my training set 10 times. Each image in my training set is going to be seen 10 times. Okay, so I'm going to sample a batch from my, I set my model to train. I'm going to have a for loop on these epochs. Then I have another for loop, which is telling me that randomly sample a small batches of data from your data set and run a gradient descent step, okay? So here I sample images and labels with the corresponding batch index from my training data. Here I send them to GPU. That's back to your question. So device, I have set it to be CUDA, which is telling me that I need to use GPU. I say send these images and labels from CPU to GPU, because then everything is going to live on GPU. And my model, I think up there, I already sent it on GPU if I'm not wrong. Yes, right here. So my model is on GPU to device. My data is on GPU as well. Now, here is a tricky thing about TensorFlow that if you don't know, it can bother you. When we define a variable, let's say I define variable x, and this is simply a d-dimensional vector in PyTorch, this has a value and grad. So essentially, like x.value is going to tell me the value of this x. X.grad is going to tell me the gradient of whatever loss function. It's a buffer for the gradient with respect to x. Okay. I need to be careful and empty this buffer, zero this buffer, before I actually do a backpropagation, before I update the gradients. If I don't do it, whatever was here will be added to the gradient. This is a very useful feature, but if you're a novice in PyTorch, if you forget to empty your gradient descent, your grad buffer, your gradient descent is not going to work. Okay. So here, that zero grad, all that it says is that all the parameters in your model, which were defined as model parameters, all the parameters that your optimizer is going to deal with, set their gradient buffers to 0. So no issue will happen. That's an important step. Okay. And then, okay, at this point, we are ready. We sent all our images through our, we sent the batch of images that we have in our model, and we get the logits. So if I had n images, now my logits are going to be n by 10. 10 is the number of classes for this handwritten digit recognition problem. Okay. Then I say, I have my labels, I have my logits, calculate the criterion, which is the cross entropy loss. At this point, I calculate my loss. I have my loss. If all the computational graph is on the memory at this point, I need to do a gradient. I want to do a gradient descent, so I need to calculate the gradients. How I do it is by backpropagation, and I simply call loss.backward. And when I do that, all these gradient buffers of all the parameters that I have are going to be updated with respect to the gradient of my loss. We have a gradient of my loss with respect to each of these parameters is going to go in their buffer. Okay. And then, of course, I have gradient, but I haven't taken this step yet. If you want gradient descent, you need to go to the negative gradient direction. And that optimizer.step will take that step for me. Okay? And it's a good practice to keep track of your loss and be sure that like your loss goes down. So I essentially am keeping track of the running average of my loss, and every 100 iterations, I print what is my current loss. And at the end of each epoch, I go and I evaluate my model. You don't have to do this, but because this was a demo I wanted to show to you, I want to look at the performance of my model at the end of each epoch on the test set. Okay, and I do that. So let's run it. Epoch 1, step 100, loss is this much. Loss is going down. You can see it starts from 1.44. It's going down to 0.86, 0.6, and 0.45. Okay, test accuracy 91.15% at the end of one epoch. Okay, and we can let it run a little bit more. And eventually, I tested this earlier this morning. It was working to 98, 99% accuracy, depending on which run you take. And that's not the state of the, like 98 point something on MNIST is not the state of the art, but it's a simple VIT model. It's a small toy example. It's working. So that's kind of good news for us. Yeah, epoch 2, 95, and yeah, it will go up to 97, 98, something like that. Okay, so yeah, this, if we were Jan LeCun and colleagues in, I think before 1997, 1998, we would have been very happy sitting on our chairs right now because we have a accuracy 98%, 99% on this application. Okay. So now maybe we pause this because I mean it's going to keep going, and the accuracy hopefully will get better and better. But let me just pause this so we can switch to a natural language processing example. So before I do that, any question on the VIT, the vision transformer? Are we all good? Okay. So like now we're going to do a transformer on an NLP application. And I have asked ChatGPT to create a sentiment analysis data for me for movies. And this is all generated by that, by ChatGPT. So it says, look, the movie was fantastic and thrilling. This is a positive review. I enjoyed every moment of the play, positive review, an absolute masterpiece, and so on. And then there are like, I left the theater feeling upset and disappointed. Of course, a very negative review, right? And our goal is to do sentiment analysis. Was this a positive review or a negative review? Okay. And I have a training set and I have a test set. And of course, I have corresponding labels for them. Okay. So, well, first, we need to do some sort of a tokenization on this data. And the simplest thing that I can do is I can build a vocabulary based on the unique words that were used in this data set. So my vocabulary is not the entire dictionary because I wouldn't have been able to train it in the demo, right? So what I'm cheating a little bit and I'm saying that the training set that I have and the test set that I have is the entire world of natural languages, right? And that's all I care about. Let me go and find all the words that are unique in this data set, right, for training a test, and like assign an integer to the unique words. We can say A is integer 1, absolute integer 2, absolutely integer 3, and so on. Okay, it's not the most efficient way of doing it, but hey, it's just a quick demo that we want to see if it works or not. So then, of course, I need to be able to go from text to integer, and then from integer back to text. So this is what I'm calling encode text and decode text. It simply looks at that vocabulary. If it finds it's a hash table that sends the word into the integer, and if you give it the integer, it's another hash table that gives you the word. So that's all that there is. And what I'm going to do, because I want to train this efficiently, I'm actually going to get a fixed context length, and I'm going to make that context length to be the maximum length in my training data. And if there is a smaller reviews, I'm going to just simply pad them with 0. Okay. So, for example, here you immediately see. Okay. I don't know if it is large enough, but you see an example encoded sentence. It gives me a bunch of integers and zeros. So zeros are the like where there is no token. And then if I decode it, it says the movie was fantastic and thrilling. So there is 83, movie is 60, and so on. Okay. So now I have turned my sentence into bunch of integers. And I create my data set here. Essentially, I put my train and test data as well as the a data loader that can sample randomly from my training data set so I can train my model on it. So this part creates the data for training. So I have the data. Now I need to define the model. And for the model, it's an encoder-only transformer because we are not doing generative modeling. We are simply doing sentiment analysis. It's a classifier at the end of the day. So we embed the input. We have a positional encoder. We add dropout. Then we go through the different layers of encoder layers and add them all together. Then like compose them all together. And then normalize the output. Here, I told you that VIT uses a CLS token for classification. I don't have a CLS token in this problem. This is not VIT, this is sentiment analysis. Input is a bunch of words or bunch of tokens. Output is a bunch of tokens. If I want to learn a classifier on bunch of these tokens, what can I do? But there are many things that I can do. I can potentially concatenate all of these together and apply a classifier to their concatenation. But that's not the smartest idea because the lengths of input can change, and like the length of output will change, and I can't learn a fixed classifier on it. One thing I can do is to use a global average pool. Simply average all those z's that we were looking at before into a fixed dimensional vector instead of a CLS token. And use that fixed dimensional global average pool, send it to the classifier for classification. Okay? And that's exactly what I do here. By the way, this is a very interesting research question. Should you use the CLS token or use some sort of a pooling mechanism? And the community is kind of torn between these two. Some say actually using pooling mechanisms is better than CLS token, but maybe that's for another day. Okay, so we do the pooling, and then we send these pooled tokens into our classifier head and get our logits out. So again, I need to instantiate my model, print my model, define my loss function, define my optimizer, and then I go in my training loop. I do 100 epochs because this is a very tiny data set that I have created. And we train the model. See, it works very fast, and the error goes almost to zero very fast because it's like a very small training set that we have. And so at this point, we know that we are overfitting to the data significantly, right? Like, so if you look at the predicted labels for the training set and the predicted labels predictions and the labels, we see that they are 100% aligned. Yeah, perfect. The training performance. And then if you do it for the test, it's actually doing a fairly good job, right? Surprisingly good job. Of course, it's making mistakes, but like it is only making a mistake on one. So now I don't know, like if you go and be the test, maybe it's because the test set is also generated by ChatGPT, and like it's kind of using very similar words. If it was actual reviews, we wouldn't have this, because you shouldn't expect generalization training only on 20 reviews. You shouldn't expect 90% generalization, 90-something percent generalization. But nevertheless, for this small data set that we have, it seems like it's working pretty nice, right? And yeah, so given that we're almost at the end of the session, I just briefly mentioned that I also added here for your own review, like an encoder-decoder model. It downloads, this is part, like originally was demo by Andrei Karpathy, who's a fantastic, phenomenal instructor. We are downloading it, I think, from his GitHub page. We are downloading this data set that includes the text from Shakespeare, all text from Shakespeare. And then what we would like to do is to do the next token prediction. Give a block size of input to your model and ask the decoder to predict what is the next word. And if you're able to do this, then you will eventually learn a model that can get nothing, or like a very simple prompt, a Romeo, colon, and then it will start completing like Shakespeare would have completed it. Okay, so here you have the data set and the model and everything. It just takes a while training, and I try to make it make the training so much faster and only train on a very small portion of the data. But if you do that, like it generates things. For example, it says first citizen shreds accounted ye, right? Like it doesn't really make that much sense. The model is small. The data is not, the model is not trained very well. But if you have time or GPU, you can play around probably and do it on your own time. So you should have access to this as well. That's all I have. All I had for the day. I'll be happy to take any questions if you have 5 minutes.
Yes, it's going on.